Today we're going to be learning about the differences between strong acids and weak acids. To start, let's learn about general acids. Acids are substances that have lots of H pluses in solution.
Did you check in the freezer?
This high concentration of H plus causes there to be a low pH. But broken up into acids, there are strong acids and weak acids. Let's start with looking at strong acids. We're going to use the general acid equation HA, which breaks up into H plus and A minus. In our strong acid, it's going to be completely broken up. So we're going to have the same number of H pluses and A minuses with no HA.
If I use these and I should refill it.
You'll notice that in our strong acid we have 1, 2, 3 H pluses. So we're going to call that a high concentration of H plus, which means that it will have a low pH. But over in our weak acid, things won't break up completely. We're going to have some HA mixed in with our H plus and A minus. This means that since we only have one H plus, we're going to have a low concentration of H plus. But the pH will still be low. It's not quite as low as it was with the strong acid. The way that we can look at how much an acid breaks up is with the Ka. The Ka of a strong acid is too large to measure since it breaks up completely. But the Ka of a weak acid measures how much it breaks up. So a higher Ka means it breaks up more, and a lower Ka means that it breaks up less. Let's look at these acids if we titrate them. So if we titrate a strong acid with a strong base, we're going to start out with a low pH, which is a strong acid. But at the equivalence point, it's going to sharply come up and then level off at the strong base. At the middle will be our equivalence point, which has a pH that is equal to 7. If we look at why that is, at the equivalence point, we're going to have H plus is equal to OH minus from our base. So these are going to cancel, which will leave us with our A minus. Since this is a strong acid, A minus does not cause any pH change. And so we're just going to have pH of water, which is equal to pH of 7. Over our weak acid, we're going to start with a slightly higher pH, and it's going to diagonal up. Then when it reaches the equivalence point, it's going to go sharply off and level up at the strong base, just like the strong acid did. Here we're going to have the equivalence point, but the pH is not going to be equal to 7. The pH is going to be greater than 7. Let's look at why that is. At our equivalence point, the same as with the strong acid, we have H plus is equal to OH minus, so they cancel. But the A minus in a weak acid has some basic properties. So we're left with A minus, which is a base, and bases have a pH that's greater than 7. Another thing to look at with these two acids is how much base it takes to get to these two equivalence points. You might guess that the strong acid needs a bit more base, but as long as we have the same concentrations, we need the same amount of base. You can think of it that there's as many H's in this as there are in this. And as we add OH minuses, the HA will break up to get H pluses to satisfy the OH minus. Another important property of the weak acid titration is the half equivalence point. This half equivalence point is where the concentration of A minus is equal to the concentration of HA. This is where our Ka becomes really important, because at the half equivalence point, the pH of our solution is going to equal the pKa, or the negative log of the Ka of our weak acid. This is also a buffer solution since we have a weak acid and its conjugate base. A buffer solution means that it will resist pH change. Let's do some practice problems with figuring out the pHs of strong and weak acids. For our strong acid, we're going to use 0.1 molar HCl, and we're going to be looking for the pH. We know that HCl will completely break up into H plus and Cl minus. And we also know that the Cl minus will not carry any acidic or basic properties, so we're left with just the H plus. And we know that pH is equal to the negative log of our concentration of H plus. And we know our concentration of H plus is 0.1 molar, so we just plug that in, and the pH will negative log 0.1, which is equal to 1. Not very difficult. Over in our weak acid, we're going to have 0.1 molar HSO4 minus, which has a Ka of 1.02 times 10 to the negative 7th. We know that this will not completely break up into H plus and SO4 minus, and that this SO4 minus might have a slight basic charge, basic properties. So we're going to put this into an ice table with the generic acid. So we're going to go HA breaks up into H plus and A minus. We got our initial, change, and equilibrium. So for our initial, we start with 0.1 molar of our HA, no H plus, and no A minus. Then as the reaction proceeds, we're going to have minus X, HA, then plus X for our H plus and A minus. So at the end, we're going to have 0.1 minus X, X, and X, which that we can then plug into our K expression. Ka is equal to the concentration of H plus times the concentration of A minus, those are our products, over the concentration of HA, which is our reactants. So if we plug that in, we have 1.02 times 10 to the negative 7th is equal to X squared over 0.1 minus X. Because this right here is a negative 7, and 7 is bigger than a negative 5, we can assume that this X is going to be really small, and so we won't have to worry about it. So then we can simplify our expression to X squared over 0.1. We multiply this by 0.1 and this by 0.1. Then we can get 1.02 times 10 to the negative 8th equal to X squared. Take the square root of both sides, and you're going to get 1.01 times 10 to the negative 4th. Now, this is equal to X, so we realize that we can plug this back in for our concentration of H plus at equilibrium. And our pH, again, is equal to the negative log of the concentration of H plus, which is the negative log of 1.01 times 10 to the negative 4th. If we do that math, then we're going to get the pH is equal to 4. For a practice problem for you to try on your own, we're going to have 0.05 molar HBr, which is a strong acid, and 0.1 molar acetic acid, which has a Ka of 1.8 times 10 to the negative 5th. You can pause the video now to work this out on your own, and then I will show the answers.
Are you going to Badger Boy State?
So you can see the work through here. Taking the negative log of the 0.05 molar will give you a pH of 1.3 for the strong acid. Then over here for the weak acid, you can see my ice table and plug that into the K expression. Again, we can assume small for minus X and then multiply each side by 0.1, and then take the square root. That'll give us the concentration of H plus at equilibrium. Then we take the negative log of that, and you'll get a pH of 2.87.